Okay, any questions about the syllabus? Questions about the syllabus? Everybody clear on the guidelines and expectations for the course? Recommendations for the course? Okay, if you want my recommendations, they're there. Okay. One thing I mentioned is writing down your questions. Writing down your questions, getting them answered. Specific questions. Okay. Being very organized. All right. There's office hours requirement. And that's when you come to want to talk about material. You can stop by and talk about anything anytime. Okay. But if you want to come by and talk about material, I have certain expectations. Okay. This is because the goal is to help you. I can't help you if you come by and you can't tell me what you need. So you need to think about what you want to come ask. I'm recommending, okay, write it down. So when you get there, you have a list. Okay, and you don't get there and, oh, I forgot to ask that. Okay, and we can knock it out and get everything answered, and there we go. All right. I recommend you write things down. However, I recommend like an old-fashioned composition notebook. You can also use this as notes to self, maybe a journal, things you want to accomplish this day or this week. All right, and you don't have to always, oh, I forgot to ask that, or I forgot to do that type of thing. All right. So organization. Organization is important for organic chemistry because there's lots of material, lots of things. You're doing lab. We got lecture. Okay. So I'm recommending you be very organized. Anybody need such as this? You get these for 50 cents at Walmart. Anybody need one? Kind of keep a journal or anything? No? Okay. Let's get started with material. Any questions about previous stuff we did? We left off with, we were doing some low structures, CH4O. Yeah, we did a structure. CH4O. We did that one. Then we did C2H6. Yeah. Heavy atoms first. Yeah, we filled the valence of carbons here. Yeah. Here, 20 valence electrons. Is that right? There should be 16 here. 18, 20. Is that right? Is that where we ended at? Good-looking compound here. Carbons, octet, octet, oxygen, octet, standard bonding, H with duets. What type of compound is that? Functional groups. We did it yesterday in lab. We'll do it this afternoon with the other half for you guys. Functional group here. Alcohol. Oh, we got an alcohol here. 2-carbon alcohol. Can we do another structure? Anybody get another structure for this formula? What'd you get? What'd you get? What'd you get? Where's it at? Okay, okay. Instead of bonding the 2 carbons together, let's put the oxygen in between the 2 carbons, yeah? We can then fill the valence of carbon with our available H's. How many we got? 6. Wow, that seems to just fall into place. Each carbon needed 3 H's. Or 3 somethings. That's 16 valence electrons if you count them. We got 20. What do we need to do? 18, 20. Things just fall into place if you know some common approaches and systematic approach. Now these also are kind of small molecules, but I'm giving you a systematic approach. We started with number of valence electrons, and this is a Lewis structure. All covalent bonds are shown with the dashes, and then all lone pairs are shown. We also need to be able to show charge, or need to show charge for a complete structure. But there's no charged atom here. Structures with double bonds, CH2O. By the way, what's the relationship between these 2 compounds?
They're constitutional isomers.
Constitutional isomers. Got the same formula, but different connectivity. Things are connected different. Here the 2 carbons are connected to each other. Over there the 2 carbons are not connected to each other. That's called different connectivity. Constitutional isomers. Same formula, different connectivity. You know, this had to be discovered a long time ago. Chemists thought that one formula was going to be one compound. But They learned that no, one formula can have different compounds. What does it mean to be a different compound? Largely different chemical properties. Okay, these have very different boiling points, solubilities in water, et cetera, different. Yeah, very different. Question.
And the oxygen was on the other side, yeah, it was on the left, would that still be considered constitutional oxygen?
No, that'd be the same compound.
It'd be the same company.
I mean, I can turn this any way I want.
Yeah.
Okay, which hand is this? My hand is my right hand? Yeah? Okay. How about now? Which hand is that? How about now? It's all the right hand, yeah? Okay. As long as it's the right hand, you can draw it any way you want. All right? Constitutional isomers. DUS, we talked about it yesterday afternoon. We haven't, okay, other half no, but can you do DUS here? Yeah, think about that. Apply that to any molecules you see, so you're practicing DUS, functional groups. Okay. CH2O. That's one DUS. I'm telling you that because usually I don't do DUS in functional groups early like we did yesterday, but doing that for the first time. How many advanced electrons in CH2O? Well, carbon has 4. Well, two H's, that's another 2, that's 6. Oxygen 6. 12 valence electrons. Okay? Let's bond the heavy atoms. Yeah? 2 H's. Let's fill the valence of carbon with H's first. I recommended that. We won't worry about bond angles yet, but eventually we're going to have to advance to that. Do we have another H to put here? No. Carbon's not good. It does not have an octet. How many valence electrons? 12 valence electrons. 2, 4, 6. What can we do next? We can put lone pairs. Lone pairs, at this point, you want to put them on the more electron-demanding atom. We want to ultimately, when you're filling octets, you want to make sure that these guys over here have the octet first. They're more electronegative, more electron-demanding. Let's satisfy the oxygen first. Now, putting the H's on carbon, that was sort of me just telling you that's a wise thing to do. How can we fill the valence of oxygen? Let's just put lone pairs around it. How many can we put around it? 2, 4, 6, 8, 10, 12. Does the oxygen now have an octet?
Yes.
Yes. 2, 4, 6, 8. You count that as 2 as being shared. Oxygen now has an octet. Are we done? Is that our good structure?
No.
All the valence electrons are up there, but it's not a great structure, mainly because carbon doesn't have an octet. That's kind of a critical thing for getting good structures. There's exceptions. The first goal is sort of, let's try to get everything with good octets. Well, you want to put another H up here? Obviously not. It's not in the formula. How about another lone pair? We have no more electrons. So what can we do here? We're going to have to ask this oxygen to share. And what we're going to do is, we're going to do first mechanism arrow. We're going to say these electrons need to move in here as a bond. We're not saying the lone pair is going to jump to become a lone pair on carbon. We're moving it in as a bond. Now what does this arrow mean? I just told you, but let's show it. It means we now have, as a result of that electron movement on the board, an additional bond between the carbon and oxygen. That's what that arrow means. How many lone pairs on oxygen now?
2.
Just 2, because the other one moved in as another bond. And the other bond, we call it now a double bond. And we'll talk about this. It consists of a sigma and a pi. At this point, it's a level 1 introduction. Still the same number of valence electrons. What about the structure now? Does carbon have an octet now? Yes, 2, 4, 6, 8. Octet. What's standard bonding for carbon? 4 bonds, no lone pairs. That's what you got there. It's 4 bonds, no lone pairs. Double bond is 2 bonds. Oxygen, does it have an octet? 2, 4, 6, 8. Yes. Standard bonding for oxygen? 2 bonds, 2 lone pairs. Everything's standard there now. Systematic approach to get to a good structure. And here's a good structure. And if you know DUS, you see how many DUS? Just 1. Okay? Again, the other half of you will talk this afternoon. 1 DUS. I told you that. So there's a good structure. This is not as good. And this would be the preferred structure, most commonly structure that is shown. Charge. Okay? Arrow movement, very important. Hugely important. Repositioning electrons. Okay? It's how we do it. And you're going to be tested on use of arrows. Understand the arrows. All right, what does arrow mean? WDAM. These are actually resonance structures. Okay? Well, one of these is not complete. This structure is actually not complete. It's not good, but it's also not complete. What are resonance structures? We will mention this many times. Resonance is really not covered by me until test 3. Many books and instructors do resonance. All of resonance test 1. I think that's a little bit too much. You guys need to have some time to become more used to structures and some basic hybridization. And then we'll get there. But we have to mention resonance a good bit before we officially cover it. What are resonance structures? Resonance structures is where the only thing is moved is pi electrons. Okay? When we went from here to here, did we move any atoms? No. Only moving pi electrons. Structures differ by different placement of pi electrons. Now we will build upon that simple intro definition. Alright? But guess what? I'd recommend starting reading about resonance structures. I'm telling you, it's going to be hugely important along the way. And we say that this is the best resonance structure. Okay, back over here, this is missing something. Is this a standard oxygen? No, and I told you if it's not standard, it's probably going to have what?
Charge.
A charge. Indeed it does. What's the charge of this oxygen?
Negative. It's negative.
It is -1. You know how to determine a charge. Okay, this is how I do it. How many electrons does this oxygen own? Now that's different from an octet. It's got 8 in terms of sharing, but when I say own, it's like, okay, this bond was made by 1 electron from oxygen, 1 electron from carbon interacting to make a 2 electron shared covalent bond. But the oxygen brought 1 electron to the dance, the carbon brought 1 electron to the dance. How many does the oxygen originally own? It owns its lone pairs, 2, 4, 6. And it originally owned one of these. That's 7. How many is oxygen supposed to own? 6. Group 6. 6. It's got 1 more than it's supposed to. If you got an extra electron, your charge is going to be negative. That's a formal charge, negative. Okay, how many does this carbon own? 3. How many is it supposed to own? 4. It's missing 1. If you're missing an electron, what's your charge going to be?
Positive.
Positive. Whenever you show charges, you want to show them very close, as close as possible to the charged atom. Okay, that's the way we do it in organic chemistry. In Gen Chem, you like put things up in the corner or stuff. Many rules to resonance structures. One thing is, resonance structures always have the same charge. Net charge. What's the net charge of this?
0.
Neutral. Net charge of this?
Neutral.
Well, it's neutral. This, okay. But we knew it was neutral. How do we know this was neutral from at the very beginning?
And the formula didn't have a charge?
Because why? Because we started with what? We started with that, right? How do you know that's neutral?
No charge?
Because there's no charge shown, okay? If that had a charge, it needs to have been shown right there with that formula, okay? Unless you, I mean, you could be said, okay, do you expect a charge here? It could be another type of question, but typically if you're given a formula, charge needs to be shown or the formula is kind of misleading or incorrect or incomplete. Okay, we have a need for a double bond here. We got one DUS. Again, a systematic approach. We introduced charge, how to determine it. There'll be some formula for determining it in your textbook. If you want a formula, you can get it from your textbook. I did the formula, but I didn't just plug numbers. I tried to explain what the formula is doing. Okay. HCN, how many valence electrons?
10.
4, 5, and 5, what, 10? Okay, let's bond the C and the N. Everybody agree we can start with that? Where do you want to put the H at?
Connected to the
Siemens
carbon.
recommends on carbon. Well, everybody recommends carbon. H is on carbon is a great place to start. Could we get a structure by putting the H on the N? Yeah. Possibly you might could, but it's going to be more of a rarity structure. The more common ones are going to have H's on the carbon. I'm just telling you that.
10 total.
Well, no more H's. I got 2 4 valence electrons. Next, we're going to put long pairs. Where do you want to put them? 1, 2. Okay. Now I've got all the electrons up there. Is nitrogen good? Yeah. How about carbon? No octet. How can we get an octet?
Triple.
Well, maybe eventually, but systematically, let's take it one step at a time. Because what is important here is to learn a process, not sort of just, I mean, how did you know triple bond?
Well, because carbon likes 4 bonds and nitrogen likes 3
But
bonds.
how do you know? Is it because it says triple bond there? You got to know, okay? If you saw some other example, you're just going to automatically know triple bond? I don't think that's the best way to, I think you need to have a systematic approach to get to that triple bond, okay? That's what I'm showing you here. How can we get carbon more electrons? You got to ask over here to share. We have no more to put up there. What we can do is, these electrons, we can move them in here. What does that arrow mean? Okay, it should mean something. What does it mean? It means it moved in here to become what?
Double.
Those 2 electrons are now sitting between the N and carbon as a shared covalent bond. 2 lone pairs remaining on nitrogen. That's what that arrow means. Now we have this structure. And those are resonance structures. Because all we did was move pi electrons. Are we done? Is it a good structure? What do you want to do next? Let's ask nitrogen to share again. These electrons can move in here and make another bond, and that will look like what? Now we have triple bond and 1 lone pair left on nitrogen. Yeah?
I had a question about the placement of the arrows. What if we put the arrow from the electrons to the bond itself? Would that be incorrect?
Electrons to what bond?
To the single bond that was right next to it.
Yeah, that's
Say
not good.
it becomes a
What I'm
double
saying
bond.
here is these electrons are moving in to make a bond between nitrogen and carbon.
Okay.
I mean, the arrow, preciseness of the arrow is important. It's a good thing to be looking at. And, I mean, I'm doing it like this because I think this is how it should be done. Okay? And arrow movement will be a huge thing. That's why I had to develop the little WDAM. Because when I'm grading, I can't say, I don't understand what the arrow means. It's So WDM, that means what does arrow mean? And if you do use an arrow incorrectly, you're going to get a WDAM. So very important. But why is it important? Not just because we want to do it. It's important because it's going to help us do chemistry and understand what's going on. That's why it's important. Okay? The students who learn arrow movements called arrow pushing. Okay, you find books on just arrow pushing. This is how you do chemistry and understanding. That's why it's used. Okay, that's why I'm doing it here. We see what's moving on, going here. Okay. Now we get to this. You like the structure? Octet. We end up with a triple bond, and this is the best resonance structure. This is the structure usually for HCN. We could draw a structure with the H over here, but I'm not going to do that because it's less common. We got a good structure here. Do we have charge over here? What's the charge of this carbon? Positive. That's negative. What's the charge of this carbon? It's actually 2 plus, and this nitrogen is 2 minus. All these structures are net neutral because the formula is net neutral.
So, if you were to like put 2 arrows on this, how do you want?
You could. I would understand what you're doing. Once you learn, you can sort of on your own do it. You know what you're doing, it's fine. But, you know, a lot of questions ask you to show all resonance structures, and so you would be bypassing this one. So just make sure you know what you're doing. Usually you do sort of one at a time. Or you may do, when we do reactions, we can do 2, but it'll be maybe 1 here and then something over here. But you'll pick it up. So we ended up with a triple bond because with the lack of the valence electrons, we have to do some sharing here to get good structures for both of them to achieve noble gas configuration. More sharing, triple bond sharing. All right? Systematic approach though. And this has 2 DUS. Okay? Yeah? Again, half of you know this better than the other half of this. But I'm just telling you that. We've already done formal charge. Carbon with 5 bonds, not on this blend. What about silicon, below carbon? Phosphorus, sulfur. Those guys can have more than 4 bonds because they have d orbitals. Okay? And you will see what's called expanded octets. We talked about this in Gen Chem. Okay? Like in sulfuric acid, the sulfur typically, well, you can draw different resonance structures. You can draw one structure with the sulfur just having an octet, but the more common structure has more than 8 around sulfur. I give you a page in the other handout, the functional group handout, that talks about expanded octets. Okay? You should read that on your own. Okay? All right. It's some important information, just to know that's sort of the exception. We'll also see compounds that do not have an octet, because they can't. Okay? Like boron. A lot of boron compounds, or aluminum, when they start acting organic, they can't achieve an octet for various reasons. All right? We'll see some of that along the way. Resonance. We introduced resonance. We just repositioned pi electrons. Yeah. Functional groups. We'll do that this afternoon, as well as DUS. That handout, those 2 topics, we did that yesterday, and we'll do that again this afternoon in the lab. After we check in, we'll go downstairs for the lecture. Okay. We'll also mention IR during that time. Functional groups. Secret advice. You guys like secret advice? Yes. So I'll try to give you some. Yeah? Closer look at covalent bonding. Hybridization. where we're starting with? Methane, Sp3. Methane is just CH4. Okay? That's just one carbon with 4 H's around it. So you should find, for drawing basic Lewis structures, okay, that's what we're doing here. These are pretty small formulas. Okay. This practice should be practice in your textbook. Okay. And there's practice in my workbook. All right. CH4. Now, of course, we would have just drawn it like this. Hey, that's a good structure. But what types of bonds are these? What type of geometry is here? What are the bond strings, bond links? Okay, so let's get into more of that detail. First thing is to look at hybridization. And this is going to be Sp3. Where does that come from? Well, it kind of starts with, okay, how many electron regions around the carbon? 4. 4 bonding regions. And 4 regions are going to be spread out the best way in what geometry? Tetrahedral. Okay? Because these electrons kind of repel each other. It's amazing that 2 will come together and bond. So there are some good things. But also electrons kind of repel each other. And when they repel, they want to spread out as much as possible, and tetrahedral is the best way for them to spread out. That's the same way if I brought in 4 balloons, maybe were kind of little long balloons, and tied them together at the tie point, all 4. You know how they would spread out? Tetrahedral. This is kind of just nature. Okay? Just like the balloons, the electrons and the bonds spread out that way. So, what is ground state for carbon? We're looking at hybridization of the carbon here. The H is not hybridized because the H is only a 1s orbital. Hybridization is where we're mixing orbitals. H only has 1. There's nothing to mix. Okay? The carbon has what? It has the 2s, is that right? And the 2p. Yeah, ground state, we showed this before. But we can also mention again, we know that this is 4 identical CH bonds through different types of analysis. How do you get 4 identical CH bonds with these types of orbitals? 4 identical bonds sort of indicates 4 identical orbitals being used. You don't have 4 identical orbitals. Also, this looks like a lone pair of electrons. That looks like carbon to electron, like a lone pair. Carbon doesn't have a lone pair. I mean, we could say we could pair up an H here and make a bond, pair this up with an H. What do you do with this? So this setup is just not good to give us reality of what we know. Okay? So at this point, chemists are like, well, apparently carbon is bonding differently from this. How is it bonding? What can we propose?
To move in electrons.
Well, you start with maybe electrons want to spread out, and these aren't spread out. Basically, all that thinking led to this new theory, and the new theory is hybridization. And what is the theory? We got to jump right to it. We could spend a day or two talking about the history of how hybridization arose. Okay, but we need 4 identical orbitals. And what we do is, the way I tell you, is these 4, we're going to mix them all. And we're going to pull out 4. Kind of like putting them in the blender. Let's mix 3 peas, 3 scoops of chocolate, and 1 scoop of vanilla into the blender. Okay? Now we can pull out 4 identical scoops of a blended ice cream. And when we pull them out, there are going to be 4 identical ones here. What are we going to call these? Yes, we're going to call these Sp3 orbitals. Okay, 4 Sp3 orbitals. The name Sp3 just comes from the fact that what do we blend? 1 S and 3 Ps. That's what went into the blender. Now they're equal. But they're also energy here, because this is energy, right? Aren't those higher energy than this? Where is the energy of those going to fall compared to this?
Closer to P.
In between. It's like the taste. Or instead of ice cream, colors. If we blend red and white, what's the blend going to look like? Somewhere in between, kind of pink. Okay? So the energy sits in between here. I'm not getting that precise. When we do Sp2, we'll say, okay, I can ask this. Is the energy of this closer to P or S?
P.
Why P?
More.
Because more P went into the blender. It's like if I put 3 chocolates and 1 vanilla, isn't the blend going to be more chocolatey? It's all the same like that. Okay? Now we have 4 identical orbitals in our theory. Now we put the 4 electrons here, here, and here. Those are the carbon valence electrons. Carbon is 4, right? Now we're ready to make 4 identical bonds to H. We bring in an H and its electron. I'm going to bring that in as an X. Now, instead of X, can I just bring in H? This is the electron from the H. Do you remember how we did that yesterday? Wednesday? 1 electron from carbon. That's the arrow. 1 electron from H. I'm showing that as an H. That's 2 electrons. That's 2 electrons. All right? And now we just made 4 bonds to H. But we're showing carbon, and now carbon has all of its valence orbitals filled. Now it has an octet. 4 identical bonds. How are these 4 hybrids spread out? Tetrahedral. How do we draw that? Tetrahedral is 3-dimensional. Tetrahedral for me, I say 2 in the plane. There and there. Those are in the plane of the board. Not forward or not back. The other 2, though, 1 is forward. And the other one is back. And this is sort of like, that should be a little bit lower in real life. Models. This is the typical student type model. Okay. I have some that are a little bit larger for class. And we can do a tetrahedral. Let's see. Okay, kind of like that on the board. Straight up. Okay, pretend the board is here. That's drawn on the board straight up, and that way on the board. That's those 2. The other 2, 1 coming forward. Yeah? And we do that with a bolded, heavy bolded, to indicate it's kind of, and it's getting bigger as it's coming closer to you. The one going back we do with dashes like this. And as it goes away, it gets smaller, like it's kind of getting smaller as it goes away, yeah? Okay. Now again, both of these that are going forward are kind of like this. It's good enough. Really, let's look at the orbitals. We have orbitals here. What does an orbital look like? Well, we know what a P and an S looks like, but what does these look like? It's somewhere in between. Okay? Now, when you mix these, we're mixing an S and a P. I'm not going to illustrate that. Let's just mix an S with a P. Okay? This is an S and a P. The S has a phase. Let's do positive. The P has opposite phases, positive and negative. These are sort of mixing. Over here, the positive will reinforce each other. Over here, the positive part of that and the negative part of that will be destructive. And so we'll end up with something over here. The roundness of the S adds to the longness of the P, and you get sort of a little bit fatter and a little bit long. It's sort of in between. But on this side, you get something that looks like that, because these cancel each other out, but not completely. You're left with a little bit of electron density on the side called the back lobe. Okay? But this would be just called an SP, because all we blended was an S and P. I'm not going to try to illustrate blending an S and 3Ps, it gets too complicated. On the very back of this handout, I show the different hybrids relative to each other. And we'll get there. So, and when I draw these, that may look like a P, okay, because but we're doing hybrids here. The back lobe is here, okay? Hybrid. Where am I going to draw the back lobe? It gets cumbersome. Because of that, the back lobe is often not drawn. Okay, this makes your drawing a little complicated. But these are 4 hybrids spread out in tetrahedral there. What is it bonding to? Right here. We're taking this and we're showing more of an orbital view. What is this orbital bonding to? Isn't this is 2 orbitals overlap? When we say 2 electrons, it's 2 orbitals. What 2 orbitals? Sp3 from carbon and what from H? Just S. Okay, that's the H. That's just the 1s orbital. And here's where the magic takes place. You have 2 electrons there. One from H, one from carbon. The important question is, what orbitals are interacting to make this bond? Sp3 from carbon, S from H. Okay? And we can repeat this 4 times identically. I'm not going to give the detail here. I gave it up here. All right? What type of bond did we just make here?
Sigma bond.
It's called a sigma bond. What is a sigma bond? Somebody? Sigma bond. Discuss sigma bonds in Gen Chem? Did everybody hear that, guys? Everybody hear that? Okay, it's not just me. You need to speak loud, guys, because people over here need to hear you. I certainly can't hear. Too many AC/DC concerts. Okay?
It's the bond for the electron densities.
No, it has to do with how the orbitals are interacting, how they're interacting. These 2 pins, bam, I just made a sigma bond. Okay? The other way would be, I'm not going to be able to do it because they're not going to stick there. I have to have Velcro. The other way is if I bond them like that. That's side to side. That's not a sigma bond. It's called a pi bond. Sigma bond is head to head. Okay? Head to head. It's like, here's the hybrid, here's the S, and they came together like this. Not like that. Okay? That's a sigma bond. The important thing about a sigma bond is what? The bond can rotate. Okay? All right? If this was here and I rotated it, that's going to be there. Okay? Pi bonds cannot. There we go, spread out tetrahedral. You can consider this model, this is implied that there's an H here, okay, but it does show the tetrahedral nature. What else can we say here? Sigma bonds can rotate. You see, this is the outline. This is what helps me. Hopefully it helps you too. Ethene. And because things are written here, I don't spell everything out on the board. I get right to it, okay? When you're looking at what you have there, you know that things are written here in the outline. All right? Ethene is we got alkene, carbon-carbon double bond. Each carbon has 2. Adding the L is sort of a slang name approach that is there. Ethylene. Each carbon here is sp2. Okay, we'll just focus on one. The other is identical. How many electron regions? Same question, systematic approach. Okay, how many electron regions around this carbon? 3. Single bond, double bond. That's 3 regions. 3 regions are going to be best spread out how? Trigonal planar. There's no space for those three regions. Trigonal planar. So that kind of gets us to the geometry. That right there, the three regions sets your hybridization. Methane you had 4 regions, so you needed 4 hybrids. This has 3 regions, so you need 3 hybrids. In the next case, we have 2 regions, that's going to need 2 hybrids. Okay? Regions, we only need 3. So instead of putting all 4 in the blender, we're just going to put 3 in the blender and not one of these. And what's that going to give when we hybridize? Okay, I'll say mix because it's a simpler word and it's also only 3 letters. Hybridize. We blend it up, we pull out 3 identical orbitals. What do you want to call these? Sp2, 3 Sp2 orbs. What is left over? What did not go in the blender? P. Did not go in the blender, it's still there. Now, we put the valence electrons here, 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 and at this point we're going to go against one rule because instead of here we're going to put the other one here. Now we make bonds, and what type of bonds do you see over here? I see a sigma bond to H, a sigma bond to H, and a sigma bond to carbon. And I also see a pi bond to carbon. And this here is what? That's your double bond to carbon, okay? Let's see here. Hybrids, 3 hybrids, trigonal planar. 1, 2, 3. Okay? If we want to draw lines to maybe see that trigonal planar, isn't that trigonal planar? Everything on the plane of the board. By the way, we didn't mention bond angles for tetrahedra. Everybody know that? 1 to 9.5. You can't have deviation from that. That's standard bond angle there. What is bond angle with trigonal planar? Yeah, 120 all the way around. Okay, that's sort of very basic, but it's important there. What is this hybrid? This is an Sp2. Yeah, that as well. This is interacting with an H. The detail was showed earlier. This is interacting with an H. Detail showed earlier. What is this interacting with in this structure? A carbon over here, which has the same exact thing. Its hybrids are also trigonal planar, 3 hybrids trigonal planar. That is what type of bond there? It's a sigma bond. See how those 2 hybrids are sitting there head to head? This is bonding to H. This is bonding to H. Those are sigma bonds too. What else is on this carbon though? We got the hybrid framework here.
There's a p orbital.
That p orbital. It's there. I'm going to draw it longer than these hybrids. How is it positioned to the hybrids? It's orthogonal. It's perpendicular to the plane of the hybrids. This one also has p orbitals, the same exact thing. But guess what these p orbitals are doing? It doesn't look like it over here. They should be the same size. That's a little bigger. They're the same size. Guess what they're doing?
Bonding.
They're not interacting side to side. I mean head to head because how are they? They're interacting side to side. Now the way I have it drawn, it looks like they're so far apart. How could they interact? Well, that's just because my drawing is not exactly to scale. They're close enough to interact side to side. Okay? There's 2 p orbitals like this. There's interaction there. We call that a pi bond. It's like the side overlap of what type of orbitals? P orbitals. P orbitals interacting side to side. That's pi bond. Okay? The orbs. Okay? And we call this pi bond. Now the pi bond has, it, you know, don't think that's two pi bonds. That's just showing the overlap. Okay. There's overlap all through here. I just illustrated it sort of above and below the plane. Because p orbital has a node there. It's got electron density up and down. But the up and down are both interacting. That's what I've illustrated. That is one pi bond. What do we have between the two carbons? We have a sigma bond and a pi bond. Two bonds, we simply call it a double bond. Okay. But it's a sigma and a pi. So that's why when we, in the DUS discussion, we look at this and we see one pi bond. Right? So that's everybody right? There's one pi bond here. And a consequence of having a pi bond here is you can't rotate, because if you tried to rotate my hand or something, look at the fingers instead of the bond, you can't, because as this rotates, the orbital rotates. But if this is bonded, the orbitals are not going to allow for rotation. Because if you go like that, you've just broken the bond. Okay? And so it's stuck here. And those atoms are stuck. And we'll look at that more and more. The relevancy of some of these statements here as we go along. What did we cover here? Next will be SP. Okay, very important table. In the back of the other handout, you need to be looking at that, and that'll take us to bond lengths and strengths. Okay. We need to do SP. With the time we have remaining, let's say what we can say about SP. And this is going to be ethyne, an alkyne, a carbon-carbon triple bond. Graphene hybridization, that's what we did here. Now this is kind of quick. This is energy, right? Energy. But I'm big on graphene hybridization because it's, again, it's a very systematic approach. It tells you the method to get the answer. Okay? To organize your thoughts, to be able to write it out in an organized manner. Very helpful. Most books and most instructors will do a little bit of this and then never do it again. I prefer you to learn how to graph hybridization, and it will help you all the way whenever. Okay? So you'll see that types of questions. Okay, back over here, I need to ask the same questions here. Do that yourself. Okay? Systematic approach. And see how far you can get, and then we'll do it quickly on Monday. Number of regions around the carbon. Both carbons are the same. Both carbons here are the same. We're really only graphing one of them. And take a look at that table and be prepared for that. And there's some questions there on the bottom. And we go through things kind of quickly here because time is valuable. But then we come back and pull it together. And then sort of pull it together. Okay? Moving through, I'm going to move through quickly. All right? Have a good day, guys. See some of you this afternoon for check-in. Yeah, 2:30 upstairs. Yeah?